All right, in this video, we're going to look at functions. So a quick introduction to what functions represent. A function is a relationship where each value of the domain, domain sometimes referred to as the independent variable. For us, we'll pretty much just stick with calling that the x values. Each value of the domain, so every x value, matches to only one value in, it's getting a little rough here, in the range. The range is sometimes called the dependent variable, or we'll just say the y values for this at this time. So each x value matches to one y value. So you never have an x being shared by more than one y value. So an example of something that would not work for a function would be something like 1, 5 is an ordered pair on the relationship, 2, 7 is an ordered pair, 1, 6, 3, 10. So the idea here is about predictability. If I ask you, I say, okay, I'm going to give you this list of points, and I say the x value is 2, what's the y value? You could look at this list and say, well, it's going to be a 7. If I said the x value is 3, what's the y value? Well, you can look at this list and say, well, the y value has to be 10. I said, what if the x value is 1? Well, you'll notice if the x value is 1, y could be 5, or y could be 6. See, that's a little confusing. Is it 1 or is it 6? Is it 5 or is it 6? It could be either one. So that's not a function. It's still a relationship. It's not a function relationship. To have a function, each x can only match to one y. So, a more typical type of thing would be something like 1, 8, 3, 7, 4, 11, 5, 20. So if I say x is 1, you'd say 8 is y. X is 3, we got 7 for y. X is 4, you got 11 for y. X is 5, you got 20 for y. So that's a function. Now, it is not required that all the y values be different. So you could even have something like x gives us a value of 20, 2 gives us a value of 20, 3 gives us a value of 20, and 4 gives us a value of 20. That would still be a function, because as long as I told you, what the x value was, you could clearly tell me what the y value was. So if I said x is 3, there's no confusion that the y value for that relationship should be 20. So that is a function. That's a special type of function. It's called a constant function. But it is perfectly fine for the y values to be repeated. The x value just cannot match with two different y values. Another way of looking at this is domain. You're plugging domain and you're getting range, or your domain is your input and your range is your output. And so you want to be clear that if I put something in, there's only one output I'm going to get for that. I'm not going to, even if I put a bunch of different stuff and they all give me the same exact output, that's fine. But I can't put something in and get more than one output. If that happens, then that's not a function. So we don't want that to happen. We just one thing in, one thing out. All right, so another thing with functions is notation. So let's look at function notation. And mathematicians, we like to be kind of creative, and you may not feel that way, but we don't tend to leave things alone. So instead of using the letter y all the time, sometimes we'll use something that looks something like this. Now this does not mean f times x. This is an issue of notation. It's not f times x. If I wanted to say f times x, I would just write fx and I wouldn't have the parentheses here. This is read as f of x. Or another way of looking at that is f based on x. So this is the function f based on the variable x. And it doesn't have to be based on x. It can be based on anything. but that's pretty common. The one you're going to see most often, f of x. So you'd see something like f of x equals, let's say 3x minus 5, something like that. And then they may ask you to evaluate that. Let's say evaluate this, and they give you something like evaluate f of 2. But we'll notice here that your x has changed to 2. Well, what that indicates is that when you work this problem out, you change all the x values to 2. And then you do your calculation. So 3 times 2 is 6 minus 5, so 1. What this is indicating is that when you have an x value of 2, remember that's like our input, we got a y value of 1. So if I were to graph this expression, this would be one of the points on that graph, the ordered pair 2, 1. But with this notation, you don't have to limit yourself to just evaluating numbers. You can actually say, well, what is f of 3b? Well, now I can start putting other variables in place of x. So again, x has been replaced with 3b, so over in my expression, if this is my function, I'm going to replace the x value for 3b. And then I'm going to simplify that. So 3 times 3, so 9b minus 5. And I get a brand new function that instead of being based on x, is based on this b variable, whatever that is. So whatever's in this little parenthesis here, that's what you replace x with. The best way to kind of look at this is don't get hung up on the letter here. This is just a placeholder. F of something. So f of something is that 3 something minus 5. That's what this function is really saying. This function says, whatever you plug in, the first thing I'm going to do is I'm going to multiply by 3, and I'm going to subtract 5. So if you put 2 in here, I multiply by 3, then I subtract 5. If you put 3b in here, I multiply by 3, and I subtract 5. So if they said, okay, well, what's f of kitten? What's that? Well, you know, according to this function, it must be 3 times kitten minus 5. Now, I don't know what 3 times kitten minus 5 is, but again, whatever's in here, that's what goes in that spot. This x is just a placeholder. You know, instead of writing the empty box, we write x. We're like, hey, do we have anybody who's not doing anything? Can they stand here? And x is saying, well, you know, I'm not busy right now. I can stand in that location. But as soon as we have something else, we move the x out and we put that in. In fact, you can even do, if you have f of x equals 3x minus 5, we can even say, what's f of x plus 4? You know, and then you start getting in, well, I'm replacing x with x plus 4? Yeah. So don't overthink it. It's just whatever's in there goes in that spot. So you multiply it by 3. So I'm going to distribute. So 3x plus 12 minus 5. And then combine like terms, 3x plus 7. So that's how you evaluate a function with that function notation. So whatever's in that parenthesis, that's what you replace your variable by. All right. Another thing we're going to look at is the vertical line test. All right. And what the vertical line test is a tool to use to determine if you're looking at the graph of a function or not. So the vertical line test says if no vertical line, and remember vertical lines go up and down, straight up and down, no vertical line can be drawn that passes through more than one point on a curve. Then it represents a function. Okay, So here I have two very similar graphs, one going, more left and right, and one going more up and down. If I think about, well, if I draw a vertical line here, I only hit that one spot. So the question is there ever a place where I could draw a vertical line and hit more than one spot on that curve? And yeah, sure, on this one, there's lots of them. If I draw a vertical line, let's say right here, and realize I'm not using a ruler, so that's why it's not exactly vertical, but you get the idea. Here I hit 3 spots. That's more than enough. So this is not a function. It fails the vertical line test. On the other hand, everywhere I draw a vertical, let me turn this a little bit, see if I can do this. That's getting worse. All right. Okay. Erase all that. Let's try this again. All right. So everywhere I draw a vertical line. I'm having some trouble with my little pad here. But everywhere, you get the idea. Everywhere I draw a vertical line, I'm only going to hit one point on this curve. Every vertical line I draw, it only ever hits one spot on the curve. So this one is a function. And you can draw a vertical line there and draw a vertical line here. Now it's going to start getting steeper and steeper, but you have to realize there's always how much space is there between the number 3 and the number 4? Well, there's an infinite number of space. So this might get steeper and steeper, but there's always room for it to keep squeezing over a little bit and a little bit. So it might be a little bit hard to recognize that it's not exactly straight up vertical, but it does pass. This one does pass the vertical line test. All right. Say we want to graph a function. Okay. So I want to graph a function. Let's say they say graph f of x equals 3 minus the absolute value of x plus 4. Okay. So I want to graph that. Now, it would be nice if I was given some values here. And in a second, I'll show you what can I do if I'm not giving values. How do I know I've got enough information? But let's say they were nice and they gave me some values. They said, I'm going to give you -6, -4, and -2. And, okay, we'll try -5 and -3 as well. Okay, so just like when we're graphing regular equations, what you want to do is you want to just plug these in and see what happens. So 3 minus -6 plus 4. Remember your order operations, you do inside the group first, so that's -2, so that's the absolute value of -2, which would give you 3 minus +2, right? The negative is because of the negative outside, but the absolute value of -2 is +2, so that would be 1. So -6, 1, -6, 1, there's a spot. All right, and then if I put -4 in there, -4 plus 4, well, 3 minus absolute value of 0 would be just the same as 3 minus 0, which is 3. So -4, 1, 2, 3. All right. -2, absolute value, -2 plus 4. Well, that's the absolute value of -2 plus 4 is +2. So 3 minus 2 is 1. So -2, -4, -6. That's 1. We're seeing kind of a strange shape, not a line. So if we continue on, -5 plus 4. Well, that's 3 minus absolute value of -1. Well, 3 minus 1, the absolute value, is 2. So -5, 2. So -3. Value of -3 plus 4. -3 plus 4 is 1. So the absolute value of 1 would be 1. So 3 minus 1 is also 2. And so we're kind of getting this shape here And again, I'm having a little down drawing straight lines here, but this is actually a sharp V shape. Wow, worse. All right. That way, sharp V shape. Okay, and that's what that graph looks like. So real quick, let me kind of give you some general ideas of what some graphs look like, so you know if you picked enough, if you have to pick your own points, if you can pick enough points there. So here, let me use function notation, I guess, since we're talking about functions. Let's say f of x equals x. This is kind of your basic diagonal line. F of x equals x squared. It's a square. This is called the identity function, this first one. So this one is a squaring function. It has a general shape, something like that. F of x equals x cubed. The cubing function looks something like that. It's a continuous curve. It just doing my best here. It's the absolute value of x. That's, if you look at that shape that I just drew, this always looks something like a V. Well, I should say always, but usually it looks something like a V. So if I'm not getting that V shape, maybe I need to pick more points or check my calculations. Square root of x. Look at the square root graph. It looks something like that. It's like a little curve starting there and kind of going. That's usually how it looks. And then the cube root looks something like that with a back end. So it looks a little like the square root, but with a tail, whereas the square root doesn't have a tail. That has to do with the fact that if you took like the cube root of -8, that would be -2, but if you do the cube root of -4, that's not real. So 2i. We'll get into non-real things. But this is the kind of idea. X to the fourth looks a little like x squared. X to the fifth looks like x to the fifth. X to the third. X to the sixth looks like a little bit like x squared. And again, so even powers, odd powers, same thing with roots. Even roots look a little like this. Odd roots look a little. So this kind of gives you an idea. If you're not getting that kind of shape, you probably need to pick more points. All right. And then the last thing we're going to talk about in this video is domain and range. How can you determine what are the x values? Remember, that's what domain is the x values for a function. How can you determine that from the graph, and how can you determine the y values, the range? Okay, so when you're looking at this, you kind of have to split this up into two pictures. Instead of seeing this as, like for example, this curve is going down and to the right, you're seeing that. You have to kind of mentally split that up into saying, well, this curve is going to the right, and then separately, this curve is going down. And you have to have those kind of two ideas split in your head, that you can look at that and look at, is it going left or right? And then in an entirely separate way of looking at it, is it going up and down? And that's kind of how you get to the domain and the range. So with domain and range, let's say I say, okay, I want to figure out what the domain. What I'm asking myself is, how far left or right does this go, theoretically? And if you're given an image like this, what you'd want to do is assume that I'm giving everything that really matters. So notice this has a point marked here at -1, 2, but no other points are marked. So I just should assume the graph continues off in both directions, keeping the way it's going. What that means is when I'm looking for domain, I'm looking for how far left or right theoretically this could go. So, I can, and I'm just going to do it on the x-axis because, again, I want to separate this in my mind separately. So I can see, well, it's going left, it's going left, it's going left, it's going left, and then I kind of hit the edge of what the picture is showing, but again, it's only showing the relevant parts. So I should assume it continues going left, continues going left, continues going left, continues going left. And the same thing here is it continues going right, continues going right, continues going right, and then it's going to hit the bottom of my image here, but it's going to keep going because again, they didn't indicate it stopped. And so it's going to keep going right, keep going right, keep going right, keep going right, keep going right. So if I'm looking for the domain, what I'm going to say is this is all real numbers. it continues left and right. Now, there's some other ways of representing all real numbers. One way, you could say something like x such that x is an element of the real numbers. That would be a way you could say all real numbers. An alternative would be to use what we call set notation, or this is set builder notation. Use interval notation. So interval notation, you go left and right. Oh, my yellow line disappeared here. Interval notation, how far left or right it goes. So it goes all the way down the number line left and all the way up the number 9 right. So it goes all the way from negative infinity up to positive infinity. So any of those ways, you don't have to say all of them. You can just say all real numbers, or you can say, x is an element of the real numbers, or you can say it goes from negative infinity to positive infinity. All those are true. And then that brings us to the range. Okay, and so what we're looking for is how far up or down does it go. So again, now this time I'm going to be on the y-axis, and I see that my graph goes down. It goes down, and it keeps going down, it keeps going down. Now it's going down to the left, and it's going down to the right. But again, I'm separating that in my head to just say it's going down, and it's also going down. Let's continue to go down, but it stops here. It stops at this height. It never gets higher than this. So it's got an upper limit here. So how am I going to represent that? Well, one way I could say that is I could say y such that y is less than or equal to, because there is a solid dot there, so I actually get there, a y value of 2. So 2 is my upper limit here. That's where I hit the top, and then it goes down. So I want 2 and everything lower than 2 for y values. These are the y values. Alternatively, if you want to use the interval notation, you kind of have to turn your head and you say, well, it goes down forever, so it goes all the way down to a negative infinity, but then it goes up to 2, and it gets there. So we put a bracket on that interval notation to indicate that it actually makes it to a value of 2 up here. So that's how you do it. You kind of have to mentally separate the picture into a, what's going on left and right, and totally separate what's going on up and down. And if you can separate that, then finding this domain and range isn't too difficult. So like, let me go back to maybe another picture. Let's say I was looking at this one that we drew. If I wanted to say, what's its domain and range? Well, its domain, again, it goes left and right forever, right? We're not assuming it's stopping that trajectory. We can pick any x value to plug it in. So its domain is negative infinity to positive infinity. What's its range? Well, we see that it kind of tops out here, turns around at a maximum height of 3. So negative infinity up to 3. And when it actually gets there, we actually got a value that had a y value of 3. So actually it has a place to top out. So domain and range. So that's your introduction to functions.